Welcome to lecture number 20. Here's the result on the whiteboard that I proved last time. I showed that for every global functor f and for all n greater or equal to 1, various restriction homomorphisms are naturally split epimorphisms, namely restriction from an orthogonal group to the next one below, from the unitary group to the next one below, and from the symplectic group to the next one below, whereby the next one below I always mean that the smaller group is included by putting a 1 in the matrix in the lower right corner. Naturality refers to morphisms of global functors, so the splittings are natural for those. The proof was modeled on Doyle's elegant proof of Nakaoka's splitting of the cohomology of symmetric groups, and Doyle's argument really proves an analog of this for fin global functors and for symmetric groups. Today I want to give two kinds of applications of this splitting result. The first is to stable splittings of global classifying spaces, and the second is to regularity results for certain equivariant Euler classes associated to representations. I want to start with the stable splittings of global classifying spaces. I'm going to give you a proposition now that puts this in a bit more general context and that tells you that whenever such a surjectivity result holds, then you get a splitting. So here's the proposition. Let I from L to K be a continuous homomorphism of compact Lie groups. Which has the analogous property as we have here, so such that for all global functors the map I upper star, so restriction along f, which goes from f of k to f of L, is surjective. And then we can conclude three separate splitting properties. So the first is that the morphism I upper star from k to L admits a section in the global Burnside category. So for this we might want to briefly recall that morphisms in the global Burnside category were natural transformations between the equivariant homotopy group functors, and I upper star restriction along this I is a natural transformation from pi 0 upper k to pi 0 upper L. So it is a homomorphism in the Burnside category, and this is a pre-additive category, and I'm telling you that this implies that the morphism has a section in there. Second splitting property, the morphism sigma infinity plus B global I, which is a morphism from the unreduced suspension spectrum of the global classifying space of L to the unreduced suspension spectrum of the global classifying space of K. This has a retraction in the global stable homotopy category. And the third property is a stronger version of the hypothesis that we have put in. We've put in that this restriction homomorphism is always surjective, and the consequence of this is that we can also take product with an arbitrary compact Lie group, and that we can always have this being naturally split. So here's the precise statement. For every compact Lie group G, and all global functors F, the restriction homomorphism and now it's G times I, which is now a homomorphism from G times L to G times K, and then upper star, so this goes from the value of the global functor at G times K to the value of the global functor at G times L. And this is a naturally split epimorphism. So this is a little bit weaker assumption, and we can conclude that we get a stronger version automatically. Namely, first of all, we didn't assume naturality, we just assumed surjection here. We didn't even assume that it was split as a map of abelian groups. And the consequence is we can even take product with an arbitrary group, and then we can have it naturally be split epimorphism. Here's the proof. Let's start with part 1. The category of global functors is defined as pre-additive functors on some indexing category, the global Burnside category. So every object, every compact Lie group, gives us a global functor, namely the represented functor. So we apply the hypothesis to A L blank, the global functor represented by the compact Lie group L. And we conclude that I upper star as a homomorphism from A L K to A L L, and in this version it is just given by post-composition with I upper star. This is surjective. So in particular, the identity here has a pre-image, and that is exactly the section that we're looking for. Any pre-image of the identity of L is a desired section. Here's the proof of part 2. We will work with the section that part 1 gives us. So let sigma in A of L comma K be a section to I upper star in A of K comma L. Now we're going to use the representability properties of the suspension spectra of the global classifying spaces. So we proved some time ago, and we used already many times, that the pair consisting of this unreduced suspension spectrum of the global classifying space of K and the stable tautological class EK, this represents the functor pi 0k as a functor from the global homotopy category to the category of abelian groups. And now we're going to use this representability to construct a morphism. Let rho from sigma infinity plus b global k to sigma infinity plus B global L be the unique morphism in the global stable homotopy category. Such that now we just have to say where this morphism sends the stable tautological class, and then by the representability it's uniquely determined and it exists. So we have to prescribe what pi 0 upper k of rho does to EK, and we want it to be sigma upper star applied to EL. So sigma was this section, it's a natural transformation from pi 0L to pi 0K, so we can apply it to the stable tautological class of L, and this gives us a unique morphism here. And now I claim that this morphism, which will typically not be induced by homomorphism from K to L, that this morphism is the desired retraction. And then again, we're going to use the representability property, but then for L instead of K. So let's calculate what rho after sigma infinity plus I, or B global I, does to the stable tautological class of L. So if we evaluate this at EL, well, first we pull it out by functoriality. This pi 0 upper L. So this is pi 0 upper L of rho applied to pi 0 upper L of sigma infinity plus B global I applied to EL. And this is pi 0 upper L of rho applied to. And then always when we do B global I lower star to EL, this just gives us I upper star of EK. That's the defining property of this morphism, or the whatever this morphism represents. Now we're going to use that I upper star is a natural operation. So in particular, rho is a morphism in the global stable homotopy category. It's natural for this. So we can write this as I upper star applied to pi 0 k of rho of ek. Now we're going to plug in the defining property of rho here. So we get I upper star of sigma of EL. But sigma was a section to I upper star, so this composite is the identity. So this is EL. And as I said, now we're going to use another representability property, this time for L and EL. And then it says that this morphism takes the stable tautological class to itself, so it has the same effect on the stable tautological class as the identity has. And by the uniqueness in the representability, it follows that this has to be the identity. So rho composed with sigma infinity plus B global I is the identity of the unreduced suspension spectrum of L. This completes the proof of part 2. The proof of part 3 uses a piece of structure that I haven't talked about yet, because it ultimately comes from the smash product of orthogonal spectra and the associated pairings on equivariant homotopy groups, and I did not emphasize multiplicative aspects of the story in these lectures very much. So now I have to use it nevertheless, so let me briefly mention what kind of structure we have. And this is the fact that the global Burnside category admits a certain symmetric monoidal structure. Has a biadditive symmetric monoidal structure that I denote by times, the symbol for product, so it goes from the global Burnside category times the global Burnside category to itself. And this is given by the product of compact Lie groups on objects. Given by the product of Lie groups on objects. Moreover, if I apply G cross, so the functor where in one variable I fix a compact Lie group, to a morphism alpha upper star, then this is the same as G cross alpha upper star. So the notation is very suggestive because it does the expected things on restriction. There's also a similar formula for what it does on transfers, but we don't need it for this proof. But now this structure present, we can finish the argument very easily. So we let sigma again from K to L be a section to I upper star in the global Burnside category. And then G times sigma, which is now a morphism from G times L to G times K, is a section to G times I upper star, which by the property that I mentioned above is G times I upper star. And so for every f, we can apply f to G times sigma. And this gives us a morphism from f applied to G times L to f applied to G times K. This is a section to G times I upper star. So this is the desired section. And this section and its construction didn't have anything to do with the global functor f. So this section is visibly natural for morphisms of global functors in f. This concludes the proof. Here's a useful addendum to the proposition, where in the same situation as before we have a continuous homomorphism such that I upper star is surjective for every global functor. And then in this situation, the functor from the global homotopy category to abelian groups that sends an orthogonal spectrum E to the kernel of the restriction homomorphism, going from pi 0 k of E to pi 0 L of E, this is representable. And this is a very special property. If you had an arbitrary continuous homomorphism alpha, of course it would have a restriction map alpha upper star. You could look at the kernel or also at the co-kernel, and these things would in general not be representable. So this is a consequence of the fact that we have this surjectivity for all global functors. So here's the argument. We choose a distinguished triangle in the global stable homotopy category. So we start with the morphism that we have, sigma infinity plus E global L via sigma infinity plus E global I to sigma infinity plus E global K. This is some morphism in the global stable homotopy category. We can always complete it to a distinguished triangle. And I want to call this morphism Q that occurs here, and I want to call the object sigma infinity plus E global of K relative L. And then there's going to be a connecting homomorphism, and we go to sigma infinity plus E global L shifted by 1. So this is just a notation that is meant to be suggestive for some choice of cone. This is not meant to be functorial in any way depending on the data. And the notation is a little bit abusive because I'm writing it as K relative to L or K over L, but of course it depends on the I. There could well be many different homomorphisms from L to K that both satisfy this property. So this is really depending on I and not just on K and L. The notation is meant to be suggestive because this object can always be chosen as the reduced suspension spectrum of some based orthogonal space. That's why I'm calling it sigma infinity of this. So now we have this orthogonal spectrum E, so we apply morphisms in the global stable homotopy category from this sequence into a given orthogonal spectrum E, and we get a long exact sequence. And I'm going to write down a part of it for you here. So here is morphisms in the global stable homotopy category from this object sigma infinity E global K mod L into E, which was a chosen cone. Then we have Q upper star. And here we would have morphisms from sigma infinity plus B global K into E. But now I'm going to use the representability property straight away. So by evaluation at the stable tautological class, I can identify this with pi 0 K of E. The next term would be morphisms from this one into E, and by the same representability argument, this is pi 0 L of E, and then the long exact sequence would continue on both sides with shifts. And this morphism also, its representability property is exactly so that this is the morphism I upper star. And now we have assumed that I upper star is surjective, and so that means this connecting homomorphism here is actually 0, so every third map in the long exact sequence that we get is actually 0, and that means that the long exact sequence decomposes into a short exact sequence like this. And this means that the pair sigma infinity B global K mod L and the class pi 0 K of Q applied to EK. So Q is a morphism from here to here. In here lives the stable tautological class for K, so we can just take its image under Q. That gives us a class in pi 0 upper K here. And this pair represents the kernel of restriction of I upper star. That's exactly what this short exact sequence is saying. There's one more consequence I would like to draw. We have seen in the proposition that this morphism has a section in the global stable homotopy category. And in any triangulated category, if you have a distinguished triangle and one of the morphisms admits a section, then it's actually a sum triangle, then it actually splits. So if we apply this to this particular situation, we conclude that this morphism has a section, so this is the sum of this term and this term. So we conclude that sigma infinity plus B global K is isomorphic to sigma infinity plus B global L sum, which I write as wedge, with sigma infinity reduced of B global K relative to L, and this is an isomorphism in the global homotopy category. The isomorphism depends on which section you choose. You know, if there's one section, there's typically many sections, and that influences the isomorphism, but in any case, they are isomorphic. And this is what I mean by stable splittings of global classifying spaces, and they always arise from such surjectivity properties. I would like to go through some examples of these stable splittings of global classifying spaces. I want to start with a very simple example, and one that in fact we have already seen. For every compact Lie group G, the restriction to the trivial group, restriction from G to E, for an arbitrary global functor, from f of G to f of G. This is always split by the inflation homomorphism. By PG upper star, which goes from f of E to f of G, where PG from G to the trivial group is the unique homomorphism, in fact the unique map. So this is a very simple situation. So this is a very simple example of the situation that we've previously discussed, and we get out some consequences. Let's define sigma infinity B global reduced of G as a different notation for what I called earlier sigma infinity B global G mod E. In fact, in this situation, there is only one homomorphism from the trivial group in, so there is no ambiguity in the notation. Let me call this the reduced suspension spectrum of the global classifying space of G. And then we get out that the pair of sigma infinity E global reduced of G and Q lower star of EG represents the kernel of restriction from G to the trivial group from pi 0 G-equivariant E to pi 0 non-equivariant E as a functor on the global stable homotopy category, and we get out that the unreduced suspension spectrum of the global classifying space of G is isomorphic to the sphere spectrum, which would be the unreduced suspension spectrum of the global classifying space of the trivial group, which the suspension spectrum now reduced B global of G. And this is actually something we have already seen. If you did all the exercises, then you will remember exercise 7 in lecture 16, which essentially had this at its content, and now we can see this as a special case of something more general. The next example is still a very simple situation in which we get this splitting. So suppose that I from L to K, continuous homomorphism between compact Lie groups, has a retraction rho in the other direction that is itself a continuous homomorphism. And then of course we can form rho upper star, which goes from f of L to f of K, and then this splits I upper star from f of K to f of L. And we are in the situation that we've discussed, so we get this representability property for the kernel. In particular, we get this splitting of sigma infinity plus B global K is isomorphic to sigma infinity plus B global L wedge sigma infinity B global of K relative to L, which really depends on the homomorphism. So this is a very simple situation of the splitting, and the real power of the mechanism is that this splitting happens in many more general situations. For example, the splittings for the orthogonal, unitary, and symplectic groups are not of this form, except in very small dimensions. The inclusion of O of 0 into O of 1 has a section because O of 0 is a trivial group. That's an example of this. The inclusion of O of 1 into O of 2 has a retraction by a continuous homomorphism, namely by the determinant. But after that point, the inclusions do not admit retractions by continuous homomorphisms anymore, and very similarly for the unitary and the symplectic groups. So the power of the splitting result that we proved last time is that you get natural surjectivity and hence a global stable splitting without there existing a retraction on the level of continuous homomorphisms. Also, if you're in this very special situation, you already have a retraction by a homomorphism, then you would get the splitting of a global classifying spaces already in the naive stabilization of unstable global homotopy theory. So here I'm referring to something a little bit in the background. Every homotopy theory, such as unstable global homotopy theory, that I model by orthogonal spaces with respect to global equivalences, every homotopy theory has a stabilization or a naive stabilization, and that is a stable infinity category together with a co-limit preserving functor from the homotopy theory you're stabilizing, which is initial among co-limit preserving functors to stable infinity categories. This is for G spaces you would get the naive spectra and not the genuine spectra. And for this splitting to happen, you only have to be in the situation of a triangulated category. So this retraction induces a morphism on global classifying spaces unstably. So if you pass to the naive stabilization, you would have a retraction. The naive stabilization is already a triangulated category, so you could form the cone there and it would represent things and you would have the splitting already in the naive stabilization. However, for the orthogonal, unitary and symplectic groups, at least for a large enough n, these splittings will not happen in the naive stabilizations because in the construction we're using genuine transfers, and genuine transfers do not exist in the naive stabilization, but they do exist in what we call global stable homotopy theory. The main example from our present perspective concerns the orthogonal, the unitary and the symplectic groups. And in particular, we can now conclude the following. The unreduced suspension spectrum of the global classifying space of ON is isomorphic in the global stable homotopy category to the unreduced suspension spectrum of the global classifying space of ON minus 1, and then the reduced suspension spectrum of the relative version that I denoted by B global ON relative ON minus 1. Now I would like to make this object here a little bit more explicit so that in the end we see that it's actually a global Thom space over the global classifying space of ON again of the tautological representation. Here's how this goes in detail. Now we should pick particular models for our global classifying spaces. For the orthogonal group we have to choose a faithful representation. And the most obvious one is the tautological representation, and then the global classifying space comes out as this. We take morphisms out of nu n, where nu n is the tautological ON representation on R to the n. And then we divide out by the ON action, and this is the same as taking Grassmannians of n-dimensional subspaces in the varying inner product space. We also want to choose the global classifying space for ON minus 1. For this particular argument, it would be convenient to not choose the most obvious one, which would be the tautological representation of dimension n minus 1, but we choose the underlying ON minus 1 representation of nu n, and we suppress the restriction from ON to ON minus 1 from the notation, and then we just write linear symmetric embeddings out of nu n, but now we're only dividing out by the ON minus 1 action. So this is a little bit larger, a slightly wasteful model for the global classifying space of ON minus 1. It's larger than the Grassmannians of n minus 1 planes, but it's perfectly legitimate, it's globally equivalent to any other model. How about the map? Under these models, the morphism global B global I from B global ON minus 1 to B global ON. In this model, it becomes the quotient map. It becomes the projection from linear isometric embeddings from nu n modded out by the smaller group, ON minus 1, onto linear isometric embeddings from nu n modded out by the larger group. And now, in the triangulated stable homotopy category, if you remember, the distinguished triangles, they arose from mapping cone sequences. So whenever you have a mapping cone sequence of orthogonal spectra, this gives a distinguished triangle, and every distinguished triangle is isomorphic to one of these. And if we already had a mapping cone sequence on the level of orthogonal spaces, based orthogonal spaces, we could take suspension spectra and we get a distinguished triangle. And that's what we're going to do now. So we can define the B global ON relative ON minus 1. We can define this as the cone of taking this particular model for B global I, adding disjoint base points, and then taking the cone. So this is B global ON minus 1 plus 2B global ON plus B global I plus, and now in this particular model, this comes out to be the cone of linear isometric embeddings from UN mod ON minus 1 to linear isometric embeddings from UN blank mod ON. This we can rewrite a little bit. So I guess I want disjoint base points. This is also the cone of linear isometric embeddings from UN blank. And now cross over ON with ON modulo ON minus 1. Disjoint base points, so these two things cancel here. Two linear isometric embeddings from UN blank modulo ON plus. And now I can put the linear isometric embeddings out of UN blank, comma, crossed over ON. I can pull this out of the cone because it's a construction that commutes with colimits and products with spaces. So this is going to be L of UN blank cross over ON. And then the cone of ON modulo ON minus 1 plus 2S naught. This is ON equivalently homomorphic to the unit sphere in R to the N, the unit sphere in the tautological representation. And if you take the cone of the unit sphere plus 2S naught, you get the one-point compactification. So this is L of Vn blank cross O of N S nu N. If these kind of rewritings seem familiar to you, then you're perfectly right, because we used a very similar kind of rewriting in lecture 8 when we analyzed the rank filtration of little m capital O, and when we identified the subquotients in this rank filtration with suspended suspension spectra of global classifying spaces of the orthogonal groups. So this gives a specific model for this relative term, B global ON modulo ON minus 1, as a based orthogonal space, and then you can take the reduced suspension spectrum that gives a particular model. And now I claim that this should be thought of as a global Thom space. Why is this? So note that if we plug in an inner product space, if I take L of Vn, L of nu n V plus smash over ON with S nu n. So this should have been plus smash over ON. So if I take linear isometric embeddings from nu n into some inner product space V plus smash over ON nu n, this is the Thom space of a vector bundle of the vector bundle with total space is L of nu n V cross over ON with R to the N, or I guess I want to write nu n for this, projecting onto L of nu n V modulo ON. And this is just the Grassmannian or canonically homomorphic to the Grassmannian of n planes over V. And because this holds for every V, we're entitled of thinking that this is a global Thom space over a global unstable space. And so the way to think of this is that B global O of n relative to O of n minus 1 is the global Thom space of the global vector bundle over the Grassmannian is just the global classifying space of ON associated with the tautological representation. And because of this, I would like to use a notation that is often used in this context. So when people have a vector bundle over some base space, then the Thom space is often denoted the base and then 2 the exponent of what the bundle would be called. And so this motivates the following piece of notation. Instead of global classifying space of ON relative to ON minus 1, I want to write global classifying space of ON, and then to the exponent nu n. And this means that this is a representation. The representation gives us a global vector bundle, and I take its Thom space. And that all in a way that varies continuously with an inner product space V, so it's actually a global Thom space. In the new notation that I just introduced and tried to motivate, this splitting now takes the following form: sigma infinity plus E global of n minus 1. This hasn't changed. And for this, I have written sigma infinity and then E global of ON, but now it's not this space, but rather the global Thom space associated with the tautological representation of the group. So this splits up. One of the copies is the global classifying space of the next smaller group, so we can split this up again, split up again, and we inductively arrive at a complete splitting. There's an isomorphism in the global stable homotopy category. The suspension spectrum unreduced of the global classifying space of ON splits up as a sum, or the wedge, from k equals 0 up to n, and then these global Thom spectra, or rather their reduced suspension spectra. E global O of k, and then the global Thom space. K. The actual statement is of course a little bit better. We are not only proving that there exists a splitting. This all came eventually from the splitting of the restriction map ON to ON minus 1, and there we constructed an explicit one. So this is a little bit better that we can actually nail down the maps from here to here that realize this splitting. There's also a way to go to the co-limit. So we recall the orthogonal space little b capital O that I talked about in lecture 8. So this was an unstable object, an orthogonal space, such that little m capital O is the orthogonal Thom spectrum over it. So this had values. B O of V is the Grossmanian of V-dimensional subspaces in V plus R infinity with specific structure map that we discussed in lecture 8. Something that I also proved in lecture 8 is that this, as an unstable global homotopy type, is actually a homotopy co-limit globally over n greater or equal to 0 of the global classifying spaces of ON. And moreover, the transition maps in this co-limit system are exactly maps that realize B global of IN. Now we take unreduced suspension spectra of this unstable global equivalence. We get a global equivalence. And at every n, the inclusion splits. So that means we can pass to the co-limit and get this kind of splitting for n equals infinity. So we get as a corollary that sigma infinity plus of BO is isomorphic in the global stable homotopy category to the wedge now k greater or equal to 0, and then sigma infinity global classifying space of OK, and then the Thom space for the tautological representation. As I mentioned a bunch of times, this statement, this splitting, and this splitting at this level have analogs for unitary groups and symplectic groups. Also, in those analogs, you have to replace the tautological representation of ON on R to the N by the tautological representation of UN on C to the N, and you have to take C linear isometric embeddings, and you have to do the same with the H to the N and SPN, where H is the quaternions, and quaternionic linear isometric embeddings. Let's recall that there is this forgetful functor U from the global homotopy category to the non-equivariant stable homotopy category. We had a whole lecture on this functor and its adjoints and what the adjoints do. This is a functor of triangulated categories. It's an exact functor. It preserves distinguished triangles. It also preserves arbitrary sums. In particular, we can apply it to any sum decomposition, any splitting here, and we get a splitting out in the non-equivariant stable homotopy category. So in particular, we can apply the forgetful functor to this splitting and to this splitting. The forgetful functor U also has the property that it commutes with suspension spectra. More precisely, if you have a global space and you suspend and then you forget, that's the same as starting with a global space, taking the underlying non-equivariant space and taking the non-equivariant unreduced suspension spectrum of that. So in this slightly more precise sense, U preserves infinite sums and it commutes with suspension spectra. Moreover, the underlying non-equivariant homotopy type of B global ON is just a classifying space in the non-equivariant sense of ON. And so if we apply this forgetful functor, we get a splitting of the unreduced suspension spectrum of the non-equivariant classifying space of ON in the non-equivariant stable homotopy category as a wedge of reduced suspension spectra of certain Thom spaces. This splitting was, of course, already known, and it was proved in the late 70s and in the 80s. The first result is due to Snaith, and he proved these splittings, the analogs of these splittings in the unitary and in the symplectic cases. And a little bit later, Mitchell and Priddy proved the orthogonal case. So by applying the forgetful functor, we recover non-equivariant statements that have been known for a long time. But now we have another forgetful functor that we can apply. So if G is a compact Lie group, we also have this forgetful functor from the global homotopy, stable homotopy category to the G-equivariant with stable homotopy category. Now G is any compact Lie group. And also this functor commutes with sums. It's an exact functor and it commutes with suspension spectra. So you have a global homotopy type, they're unstable, and you take the suspension spectrum and then forget. You could have passed from the global space to the underlying G space, which in favorable cases is given by evaluating at the complete G universe, and then take the suspension spectrum in the world of orthogonal G spectra. So in particular, we get a corollary from this. For every compact Lie group G, there is an isomorphism in the G-equivariant stable homotopy category between the unreduced suspension spectrum of the underlying G space of the global classifying space of ON. Let me write B sub G of ON for this. So this is the classifying space for G-equivariant vector bundles of rank n. And this splits as a wedge from K equal 0 all the way up to n, and then the reduced suspension spectra of BG of OK, and then K. For G being the trivial group, this is the result of Snaith and Mitchell-Priddy. In the case where G is a non-trivial compact Lie group, I have not yet seen this result before, so it seems to be a new result. Another application of the splitting of global functors is to regularity results for equivariant Euler classes associated to representations. I will explain this mainly in the real case for the capital M capital O Thom spectrum. There's also a parallel unitary or complex version that I will mention at the very end. The complex Bordism spectrum MU is altogether more prominent and more important in homotopy theory than the MO version. So the complex version is probably even more interesting, but since we have mostly talked about the real version, I will go through that in detail here. So let us recall from lecture 10 the global Thom spectrum capital M capital O. This is an orthogonal spectrum and it has terms MO at an inner product space V is the Thom space of a certain bundle over the Grassmannian of V-dimensional subspaces in V plus V, and implicit is the tautological V-dimensional plane bundle over this that this Grassmannian comes with. Then there were specific structure maps that I discussed in lecture 10, and I don't want to repeat them. One of the features that I mentioned is, I didn't give a complete proof, but at least I mentioned that this is oriented, so this means it comes with Thom isomorphisms. For equivariant real vector bundles. Precise statement was given in lecture 10. So in particular, if we have a representation of a compact Lie group, so let V be a representation of a compact Lie group G, well, we consider it as a vector bundle over the one-point G space, and then it has a Thom class, which I denoted sigma G, V. So this lives in the reduced n-dimensional G-equivariant cohomology of the one-point compactification, where n is the dimension of the representation V. And being a Thom class means that it's a free generator of the graded cohomology of SV as a module over the graded coefficient ring. Associated to this comes an Euler class. The Euler class that I write for EG, V. So this lives in pi minus n G equivariant of MO, which we can also think of as the reduced cohomology in dimension n of just S0. And this is the restriction of the Thom class, sigma GV, along the inclusion of 0 and infinity. These are the 2 points in the one-point compactification that are always fixed. If the representation has non-trivial G fixed points, then this inclusion is now homotopic, and then the Euler class is actually 0. But if the representation only has 0 as the only fixed point, then this is a non-trivial class in dimension minus n, which in particular shows that for non-trivial groups G, this capital N, capital O is not a connective theory. In the theory of equivariant formal group laws and equivariant two-torsion formal group laws, a question that is often relevant is whether or not these elements are regular elements in the coefficient ring, and a regular element, I mean, is not a zero divisor. And here's a theorem that we can prove now. For every compact Lie group G, and every continuous homomorphism psi from G to O of 1. O of 1 is a group with 2 elements. The Euler class of the G times On representation that I write psi tensor mu n on R to the n is a regular element in the graded ring. Pi star G times On equivariant of MO. This notation means that we're acting on R to the n, the On acts in the tautological way, and the G acts through the character and then by scalar multiplication. So if this happens to be the zero homomorphism, then G is acting trivially, and otherwise an element is acting either by +1 or by -1, depending on where it goes under this homomorphism. This regularity result was already known for n equals 1 and n equals 2. Indeed, in the proof you will see that the key new ingredient is the surjectivity of the restriction homomorphism. And as I mentioned earlier, for n equals 1 and n equals 2, the inclusion has a retraction by a continuous homomorphism, so the surjectivity can be obtained in a much easier way. The proof proceeds in 2 steps. I first want to look at the special case where the character, the chi, is actually the trivial homomorphism. Chi is trivial. So in that case, we're looking at the tautological representation of On, and it's just restricted or inflated along the projection from G times On to On. So we consider the co-fiber sequence of based On spaces. So this is the same co-fiber sequence that has already come up a bunch of times and that has been useful before. We look at On modulo On minus 1 with a disjoint base point mapping to S0, and because this is On equivalently homeomorphic to the unit sphere in the tautological representation, the cone is homeomorphic equivalently to the one-point compactification, and then it goes on with the suspension. Now we let G act trivially on this. So then it's a co-fiber sequence of G cross On spaces, and we look at the effect in G times On equivariant MO cohomology. This gives a long exact sequence in MO upper star G cross On. And let me draw the relevant part of the sequence. So we take the cohomology here, so that is MO star G cross On reduced of S mu n with trivial action by the group G, going by restricting along here to MO star G cross On equivariant reduced of S naught, and then going to MO star G cross On equivariant of On mod On minus 1 with a disjoint base point. And then the long exact sequence would go on in both directions. So let's analyze these terms a little bit. So the cohomology reduced of S0 is just another name for the homotopy groups in dimension minus star G cross On of MO. So here we can use an adjunction. Mapping out of an induced space is the same as G cross On minus 1 cohomology of S0. So this is isomorphic to the homotopy groups in minus star of G cross On minus 1 of MO. And this becomes the restriction homomorphism. Restriction from G cross On to G cross On minus 1. And here comes the benefit of the splitting. In the proposition I told you that the splittings are inherited by taking products with groups, so not only would this be surjective without the group G, it's also surjective if there's an additional group G acting, so this is actually a surjection, and the long exact sequence splits up into a bunch of short exact sequences. How about this term? Well, the Thom isomorphism exactly identifies this with the MO cohomology of S0, and then there's a grading shift, and then we turn cohomology into homotopy, so this becomes, by the Thom isomorphism, pi minus star plus n G cross On equivariant of MO. And this map is induced by the inclusion of 0 and infinity, and that exactly takes the Thom class to the Euler class. So under this isomorphism, this becomes multiplication by the Euler class of nu n, and the implicit understanding is that G acts trivially on this. And so because of the surjectivity, the non-exact sequence is split up into short exact sequences. So what we've shown here is that the Euler class of the tautological representation with G acting on it trivially multiplies injectively, so that's a regular element, and this proves the special case. So this means that E of nu n is regular in pi star G cross On of MO. The general case can be deduced from the special case as follows. We consider the following homomorphism. That I call psi. It's a self-map of G cross On, and it sends a pair G, a matrix to G, chi chi of G times the matrix. The fact that this is a group homomorphism depends on the fact that scalar multiplications are central, so they commute with all elements in ON. So this is actually invertible, so this is an isomorphism. And it satisfies if you take psi upper star and apply it to nu n. So this was the G times ON representation with ON acting tautologically and G acting trivially. Well, if you restrict it, then the G goes to the chi and then it acts. So this is actually what we call chi times nu n. So you can get the general case by restricting the special case along a particular group homomorphism that happens to be an isomorphism. Because this is an isomorphism, psi upper star from pi star G times ON equivariant of MO to pi star G cross ON equivariant of MO. So this is legitimate to consider because MO is a global object, so we can restrict along arbitrary continuous homomorphisms. This one is even an isomorphism, so this is an isomorphism of graded rings. Also, the formation of Euler classes commutes with restrictions, so psi upper star of the Euler class of G cross ON, nu n with G acting trivially is the Euler class of G cross ON representation psi upper star of nu n, and by what we considered here, this is the Euler class of G cross ON for the representation chi tensor nu n. And an isomorphism of graded rings, of course, takes non-zero divisors to non-zero divisors, so this is a regular element because the other one was. So E G cross ON chi tensor nu n is regular because E G cross ON nu n is. This is how the general case can be obtained from the special case by kind of twisting with this character. Let me emphasize that we are really very strongly using several times the global structure of MO. The Thom spectra MO have been considered as equivariant objects since a long time, starting with work of Tom Dieck and Bröker and Hook. Typically, they were considered as G-equivariant objects for G and the family of its subgroups, and these Euler classes have been considered. I wouldn't know how to obtain this result if I didn't know that this family of equivariant spectra is really part of a global family. We have used this several times in the argument. As I said before, the complex version is probably even more interesting, so let me at least state the precise result in the complex version for you. And here it will go as follows. For every compactly group G, and every character, so continuous homomorphism from G now to U1 instead of O1, the Euler class of the G times UN representation chi tensor nu and C is a regular element in the homotopy ring. Pi star G cross UN of mu. So everything now has to be interpreted in the complex version, so we have to take the complex Thom spectrum, global Thom spectrum MU. We have to replace orthogonal groups by unitary groups. We have to replace the tautological real representation by the tautological complex representation of UN on C to the n. And this tensor product is over the complex numbers, which means it's still C to the n, that's the underlying vector space, and elements from G act by scalar multiplication wherever they go under this character. I want to end with another regularity result that we can get out of the splittings, and it reads as follows. We consider natural numbers, k1 up to km greater or equal to 1, and we let n be their sum. And then we can conclude the following result. The Euler class of the tautological representation of the product of orthogonal groups OK1 cross OKM on R to the n, so n is the sum of these numbers, is a regular element in the equivariant homotopy ring OK1 cross OKM of MO. And for completeness, let me also state the unitary version, the Euler class of the tautological representation, and now everything with unitary groups. Take the product of U, K1 cross U, Km. Now it's on C to the n, n is the sum of these numbers. So this is also a regular element, and now in the complex version. In the ring pi star UK1 all the way up to UKM, and now MU. I want to prove the orthogonal case, and the unitary case is proved in very much the same way. So the first, or the key ingredient, is that the tautological representation of this product group is actually not irreducible, at least if you have two or more factors. So the tautological representation of OK1 cross OKM decomposes into a sum, namely it's P1 upper star of mu K1 direct sum and so on up to Pm upper star of mu Km. And what are these P's? Where Pj is just the projection on the jth factor. So it goes from the product OK1 up to OKM and onto OKJ. So this is the projection onto the jth factor. Euler classes take direct sums to products. So the Euler class we care about, the relevant Euler class, is thus the Euler class of OK1 cross OKM, comma R to the n. This is the product of the Euler class of OK1 all the way up to OKM with P1 upper star of mu K1, and then multiplied all the way with the Euler class of OK1 cross OKM, Pm upper star of mu Km. Now I claim that each factor is regular because each of the factors is pulled back along a projection from the tautological representation of some orthogonal group to a product. You know, depending where you are, the product is not always written completely on the left, if I had in the previous theorem, but that is not relevant. So some factors are to the left and some are to the right. But you're pulling back a tautological representation along the projection to a product. So this was the special case of the thing where the character was actually trivial, the case that we proved first. So we're in the situation that we have non-zero divisors, m of them, and hence the product is again a non-zero divisor. So the product is regular too. That completes the proof in the orthogonal case, and the unitary case is completely analogous. This ends my discussion of the application of the splittings of global functors at orthogonal, unitary, and symplectic groups. This is what I had planned to show you today. So I would like to thank you one more time for your attention.